All right, welcome to Unit 8, which is going to study chemical kinetics and equilibrium. We're going to start here with kinetics, which is the study of reaction rates and the molecular events that result in a chemical reaction. Essentially, we're going to consider the speed of reactions for the first time. Variables that can affect the rate or speed of reaction include concentration of the inputs, which would include reactants or catalysts, which we will define later. Temperature can also affect rate, and surface area of the reactants can also affect rate. Behind all of this, we're going to be looking at collision theory. And collision theory is a theory that tries to explain kinetics by assuming that for a reaction to occur, reactant molecules have to collide and they have to have a successful collision. And in order to be a successful collision, there has to be enough energy at collision, and the collision has to have the proper orientation. So the more successful collisions you get per unit time, the faster the rate. Let's start by looking at concentration of reactants. So often the rate of reaction will increase when the concentration of reactants increase, and we think about this with the collision theory in mind. If you've got more particles, then you'll probably have more collisions. So even if your success rate doesn't go up, having more collisions mean you'll have more successful collisions, and that leads to an increase in rate. However, sometimes we have reactions where we notice that increasing the concentration of reactants either has no effect, or sometimes it even slows down the reaction. And that means that something different is happening at the molecular level than what we're looking at on paper. We're going to define reaction rate as either the increase in molar concentration or molarity of a product component over time, or the decrease in molarity of a reactant over time. And you guys took a look at this when you worked through the POGL last class. As with the reaction proceeds, we're making more product, so that concentration should go up. And as the reaction proceeds, we're going to be using up reactants, and so that concentration should go down over time. The dependency of rate, though, on concentration is going to be determined experimentally, and we'll talk about that a little later. So if we take a look at the reaction that we have here, we've got the decomposition of dinitrogen pentoxide. And we could define the rate of formation as the change in oxygen concentration over the change in time. The delta there means change, just like it does in math class. That's final minus initial. When we put brackets around a component, we do that to tell you that we're talking about molarity. So for now and forever, when you see brackets, that means molarity. If we do that over a change in time, change in concentration over change in time, we would consider that to be an average rate. So we're looking at final minus initial for concentration over final minus initial of time. So let's just imagine for a minute that we're going to graph the concentration of oxygen versus time. So if we keep in mind that our oxygen is a product in this reaction, and we want to think about how that concentration changes over time, we would expect the concentration of the products to increase. So we would expect to see a graph that shows increasing concentration as time goes by. So let's take a look at what a graph for this reaction might look like. So looking at this graph data, we have a change in concentration we have concentration on the y-axis, time on the x-axis. So if we think of change in y over change in x, which would be slope, that really represents rate, because rate is change in concentration over change in time. So if you took the slope of the curve at any one point, which would be looking at the slope of the tangent line, you would get what we call an instantaneous rate. So at any point in the reaction, you could find the rate of reaction at that time. So looking at the graph, would you define the rate as being constant for this graph? We could ask that same question by asking if the slope is constant for this graph. So since the slope is changing, since we have a curve and it's not linear, that means that the rate is also changing over time. So looking at the graph, thinking about how the slope starts off at the beginning and how it finishes at the end, would you say that the rate is getting faster or slower as time goes on? So if we think of the slope as an indication of rate, a steeper slope at the beginning means it's kind of fast, and kind of a flatter slope at the end means it's going to be slower. So this shows a reaction that's slowing down over time. And if we think back on collision theory, if we have fewer reactant particles as the reaction proceeds, and then collision theory says if you have fewer particles, you'll have less collisions, you'll have a slower rate. So because of that, many reactions slow down over time. So in your notes, I'd like for you to sketch a graph that would represent reactant concentration over time for this same reaction. This graph is showing us product concentration, and I would like for you to sketch out one. Doesn't need any numbers or anything, but just sketch out what the shape of the curve would look like if we were looking at product concentration over time. So think about if it starts high or low, if it finishes high or low, is the rate going to be constant? If the rate changes, what does that curve look like? So go ahead and sketch this out in your notes. We will take a look at your sketches when we get together next class. So there's a stoichiometric relationship between the rates of each component in a chemical reaction. We're going to use that same decomposition reaction that we were looking at before to demonstrate this. And we had already talked about change in oxygen over change in time. It's a product. We would expect that change to be positive because our final concentration of oxygen would be higher than our initial. If we were thinking about how reactants would change over that same amount of time, the reactants should be getting less. So we would expect that rate of change to be negative because our initial, our final would be less than our initial for the reactants, and so that would give us a negative rate of change. It's also stoichiometrically related. So notice that we tried to make these two rates, set them equal to each other. So if we try to set change in oxygen over time equal to change in dinitrogen pentoxide over time, the reactant will be negative compared to the positive for O2, and so we need a negative sign to make them equal. And the N2O5 would be twice as big of a number than the O2. So in order to set them equal to each other, we have to cut it in half. And so essentially we see the stoichiometric relationship kind of looks like a molar ratio. It's the same idea. So we don't have a molarity meter to measure rates, even though we're talking about changes in molarity over time or changes in concentration over time. So experimentally, if we want to measure changes in concentration, we have to measure characteristics that depend on concentration. So we might measure things like pressure if we have gases, colorimetry if our reactants or products had a particular color to them, conductivity if we're talking about ionic compounds. There's a variety of characteristics that we could measure that will give us an idea of how concentration is changing, even though we can't really measure it directly. We'll be using some of these techniques in the lab during this unit and in the next. So let's move on and try to think about this quantitatively. Let's throw some numbers at it. So we're going to develop what we call a rate law for each chemical reaction. And the rate law is an equation that relates the rate of reaction to the concentration of the reactants. And it is, again, it is determined experimentally. So we're going to give you some rate laws, but there's been some experimentation behind those that gave us what that formula is going to be. So let's take a look at the reaction that we have here. We have 2NO2 is reacting with F2, and it's going to yield NO2F. So when we do our experiments, we are observing that the rate is proportional to the concentration of NO2 and is proportional to the concentration of F2. So it means it's directly related. So the rate law that we would write when we have those findings is we would write the word rate, which is essentially going to be change in concentration over change in time. There's a K value here, lowercase k. This is called the rate constant. It is unique for the chemical reaction, and it's specific for the temperature that we ran it at. So K values will change with temperature. But for now, we're not going to mess with the temperature, and so we'll keep that kind of out of the equation. So by being proportional to NO2, that's essentially saying that the rate law is going to have the concentration of NO2 in it, but it's only got a 1 as an exponent. And so the 1 exponent is understood. So that way, if I were to double NO2 and keep everything else the same, it would double the rate. And so that would be a proportional change. And since they said it's also proportional to F2, that means F2 concentration is part of the rate law, and also with a 1 as the exponent. Because if I kept everything else the same, and let's say I tripled F2, then the rate would triple. And so our experimental observation that it's proportional allows us to write the rate law with the proper exponents for the concentrations. So reaction order is essentially what we call that exponent in the rate law. The overall order of the reaction is when you add up all of the exponents. So if we go back to our last slide, we would say that for this reaction, it is first order with respect to NO2, it's first order with respect to F2, and it's second order overall, because 1 plus 1 gives us 2. So if we come back and we look at our new reaction here, we've got a different reaction here. We're giving you the rate law that was determined experimentally, and this rate law is showing us that it is second order with respect to NO, first order with respect to H2, and that means it's third order overall, because 2 plus 1 gives us 3. So if you'll notice, sometimes it matches the stoichiometry, and sometimes it doesn't. So in this case, I had a 2 coefficient in my reaction, and I ended up with a 2 as my exponent. But that didn't happen with the H2. And again, rate laws are determined experimentally. Unless we give you some specific information, we can't just look at the chemical reaction and write it down. So you got to go with what the experiment gives you. So reaction orders are normally positive whole numbers, but they can be 0 or negative or fractions. So I want you to think about for next time, what would it mean for a reaction order to be 0? What would it mean for it to be negative? We'll talk about those next time. So we've said a couple of times now, rate laws must be determined experimentally. There's 2 ways we can do that. The first one we're going to look at it today is called method of initial rates, and then the second one is looking at how concentration changes over time.